Good morning, everybody. So I'm going to present to you common work with Genevieve. So this is the third episode of the trilogy. For those who were in Xiamen, they attended the second one, and the first one was presented at the new 3SC conference about innovation and superconductivity, and Jenny is the chairwoman of this conference. The goal of this presentation is to show you that maybe there is another way for cold fusion, which would be fusion. Why? Simply because in the beginning there was thermodynamics, fission and fusion as energy sources. But the question I would want to raise here is there, are we sure, can we be sure that we exhausted all the possibilities in thermodynamics? Okay, so this is basically the topic today. And another personal remark is that what I heard until now basically relies on known physics. I even think that quantum physicists in the beginning of the 20th century would have succeeded if they had went on with classical physics. So we need some kind of a breakthrough in the approach of problems. So entropy is interpreted today as disorder, classical thermodynamics. And if we create disorder at constant temperature, then we have heat. Disorder is viewed by mathematicians as today indistinguishability, and I presented this in Xiamen, so I will not say more about it. But this is the basic definition of what randomness is today and disorder in mathematics. This dates back to 1983 and was elaborated in Princeton University by a guy whose name is Yao. What can it mean in physics? So I refer to the Xiamen conference. And what are we going to consider for order? So what we propose is consider as order what mathematicians call order relation. This is simple, this is trivial, this is obvious, okay? This is an antisymmetric and transitive relation. And we shall consider the best possible order being total order, which means that any two elements in a set can be ordered. There is one which is less than the other, or vice versa. And what we call the most possible disorder is a completely disconnected graph. So simple math. So let us count now the number of possible orders given in a set of n elements. We set for a couple xy equals 1 if x is less than y, otherwise xy equals 0. And we define then an equivalence relation between the couples, okay, on a set of n elements by saying that two orders are said to be equivalent if there is a permutation of the elements which gives exactly the same graph in terms of order relation and in which the vertices are labeled, of course, because the labels are the names in some way of the elements of the set. Equipped with such an equivalence relation, we deduce that there are 2 to the n minus 1 over 2 possibilities for having different orders. We number these orders very naturally from 0 to 2 to the n minus 1 over 2 minus 1, like binary numbers. And for this calculation, we have assumed that the elements of the system are indistinguishable, like thermodynamicists do. So what we call entropy in this model is an equivalence class of order. It is characterized by a number between 0 and 2 to the n minus 1 over 2, minus 1. And so that our entropy decreases when the order decreases. If we want to fit with what physicists do, we just take to take, for example, the inverse of this, and we get exactly the same behavior as physics. Now, what is the link between our entropy and the one of physicists? It's unclear. Okay? I shall not answer the question here, but at least the question is worth to be asked. Is there a way to have a match? Probably a bit. It means that for some points it will match, and for others it will not, because this notion of entropy is much more general than the one you have in thermodynamics. And how does the system evolve? It can evolve in terms of entropy, because we have, I told you, a number between 0 and 2 to the n minus 1 over 2. It can evolve by steps of 1, decreasing, or more. If we have steps of 1, these are Markov processes. If we have rare events of 2 events together, it will be Poisson processes. And for the more general, it will be Levy processes, which are used today mainly by the banks or the financial stock market. Now, link of entropy with temperature. The Nernst principle says that the entropy decreases to 0 when the temperature decreases to 0. So this means that there is a link between order and temperature. Oh, I shall come back later on this for the link of temperature with order. 0 temperature, which brings us near total order, okay, because of the Nernst principle, which is the third principle of thermodynamics. And since superconductors happen at very low temperature, we can deduce that superconduction is linked with order, most probably. So if we want to have superconductors at high temperature, we must look for nearly totally ordered structures at high temperature. Is it possible or not? We think yes. So thermodynamicists are now some kind of new thing. Thermodynamicists are unable to deal with the whole universe. Okay, I made a presentation in front of the Academy of Sciences of Russia in 2010, and I was opposed the fact that I was applying thermodynamics and mainly the second principle of thermodynamics to the whole universe. It's not been proven that it works. It can be applied. So here is a proof. Let us tackle the problem in the framework of non-Archimedean space. So I made a presentation about this very quickly in Xiamen, and another one in U3SC 11 in Slovenia 2 weeks ago. And let us assume that we can describe our scale with the reals. Basically, the reals are not necessary, but any set of Aleph1 cardinal is okay. Let us make a homothetic transformation of ratio 1 over omega, where omega is the first transfinite ordinal of Cantor, and we work in this field. Yes, this is a field. Now, the laws of thermodynamics can easily be proved to be describable in a first-order logic language. This comes from computer science and formal logic. If we apply this, and if we notice that this set is a bare state, is a bare space, like in topology, so we can tile it with a countable number of finite volumes. And if we apply the theorem of compacity of formal logic, then we can deduce that the laws of thermodynamics can be applied to this whole set. If we can apply to this whole set, we just need to take the homothetic of it with ratio omega, and we go back to our system. Okay? So all laws of thermodynamics can be applied to the open system by excellence, which is the whole universe. We know the Archimedean one we have. This raises, however, this interesting question, which is linked with the construction of the serial numbers in 1974 by John Conway, because we have things which are like that, and which are kind of infinite, and which are a bit weird. And probably, in that range, we can have a bit of a different thermodynamic system. Now, the different types of orders. There are the geometric, topological, and chemical orders, which we know. And there are also the ones which are linked to fields. I don't know if you're aware, but today in physics, globally, there are 73 fields. Too many, probably. Then both fusion and fission should be linked with order, because we create energy. There is no reason why there will be something different at stake for this. Okay? So the only way for fusion is through non-Archimedean geometry, when you merge nuclei, and which are made of non-Archimedean stuff. Catalyzers are trivially disruptive agents, so I go through this. Outside chemistry, thermodynamics deals with topological and geometrical orders only, and so temperature is a partial function of orders. Now, for energy, we start from this equation. We had seen above that we can have several orders, so let's take some stuff which is built by itself, I would say, natural stuff, for example, and which has several underlying relation orders. These underlying relation orders are related by the tensor product of the orders. Okay? So what are we going to do? We are going to engineer this stuff, and in the way that the global order we obtain is this one. So the global tensor product of what existed before and what we work out. So what we are working costs energy. And the idea which is behind that is when we are going to break the order, we are going to break all the orders like a card castle, okay? And we will get more energy than it costs to make the system, okay? And this doesn't contradict any principle of thermodynamics. So we can create a new fuel and get more energy from it than we have, than it costs to create it. So is it, typically this is what could happen in what Jenny, Inco, and Jacques Dufour did in picochemistry, and which was presented by Jacques. So, introducing the action of choice now, I'm going to go very, very quickly through that. But if we introduce the action of choice like I presented it in the end, what does it mean? It means that we will have the Zermelo theorem. The Zermelo theorem implies that there is a total order anytime when we are in the system. And so we have potentially, once again, infinite energy with this model, like I showed in Xiamen for another model with an Tarassenko theorem. Okay? So if we want linear, we only need to play with the Zermelo order when it is at stake and when we want to get energy out of it. So, very high temperature superconductivity works exactly the same way. Okay, we can have a tensor product of several orders underlying, and we will avoid the saturation currents through distributing them through the different orders which are piled up, okay, depending on their number. Some advertisement for the book about non-Archimedean geometry in physics. And I thank you for your attention.
Are there questions?
People who deal with cosmological questions and general relativity arguments constantly are using the terminology of thermodynamics, if you will. They refer to temperatures and the like. So I'm not entirely sure how your earlier comments and talk relate to the completeness, if you will, of the thermodynamic concept of the application. So I may be misunderstanding where your statement about the absence of the applicability.
I didn't say the model I present is complete in the sense of God. Okay? I just say that if we take the laws we know in thermodynamics today, we can apply them as is to the global universe without any. The theorem is shown here basically.